In this lesson, we're going to learn about proving conjectures using deductive reasoning. So to start with, we have a little exploration. It says, how can the conjecture, all teens like music, be supported inductively? Can this conjecture be proved? Well, if you think back to our previous lesson, when we were supporting or proving something or validating a conjecture using inductive reasoning, we needed to collect evidence. And once we collected evidence and we had enough evidence, we could say, yes, this supports the conjecture, no, it doesn't. But to prove a conjecture means that there is no counterexample, which means that there's absolutely no way for this conjecture to be disproved. This also means that you need to collect every last piece of evidence. Now, if we look at this, all teens like music, that's pretty vague. So all teens around the world, all teens in your classroom, all teens in Canada. So a statement like all teens like music is very difficult to be supported inductively because you'd have to ask every single teen, whatever that means. And that's not always easy to do, especially if it's all teens in the world. We do have a survey in Canada called the census where every Canadian needs to be asked a certain question, and by law everyone needs to fill out the survey, but even for that one they can't get every single Canadian's data, although they try to do their best to get almost every single one. So can this conjecture be proved? Well, if you can't ask every single teen, then you're not going to be able to prove it. Can we support it? Probably. We'll collect a lot of evidence and we can draw some conclusions about it, but not necessarily have 100% this is a conjecture that is true or false. So we can write a little bit of notes on that. The conjecture could be supported inductively by collecting evidence through a questionnaire or an online survey. We cannot ask every teen, so the conjecture cannot be proven. But one counterexample would refute the conjecture. So if a student says they dislike music, then that would be enough to say that this is not a valid statement. So what is the definition of a proof? A proof is a mathematical argument showing that the statement is valid in all cases or that no counterexamples exist. A generalization is a principle, statement, or idea that has a general application. So we often use generalizations in math to help us draw some conclusions. Let's take a look at a different type of example. John discovered a pattern when adding integers. He claims that whenever you add 5 consecutive integers, the sum is always 5 times the median of the numbers. Okay, so there's lots of terms here. So consecutive meaning one number after another. So here, this first one, 1, 2, 3, 4, 5, those are consecutive numbers. And so he's saying, okay, if you add those 5 consecutive numbers, the answer, the sum, is 5 times the median of the numbers, and the median is the middlemost number. So 5 times 3 is 15. Okay, so this other one, negative 15, negative 14, negative 13, negative 12, negative 11. The median number is negative 13 times 5. That gives you 65. And let's try this last one. We can see that these are consecutive numbers as well, negative 3, negative 2, negative 1, 0, 1. The median is negative 1 times 5 gives you negative 5. So that all works out. So it says, how can you prove that John's conjecture is true for all integers? Okay, well, every single integer. How would we do that? Well, let's start with the ideas behind John's conjecture. So the median number 5 times 3 gave us 15. The median number 5 times negative 13, right? Negative 13 was the median. That gave us negative 65. And then the last median number was negative 1. Multiplying that by 5, that gave us negative 5. So his conjecture was true for all of his examples, right? Well, what if we tried a bigger number? Think of something really big. Let's say I start with 210 plus 211, 212, 213 plus 214. Well, according to his conjecture, our median number is 212, and 212 times 5 should give us the final answer. Well, let's add those all together. If you do that, just adding 210 plus 211, 212, 213, 214, that gives us 1060. Okay, well, what is 5 times 212? I need to use my calculator for that. So that gives me the same answer, 1060. Okay, so if we've tried a sample with larger integers, and we know that it's true for John's examples, but somehow we have to come up with a generalized statement, a proof that would work for any integer, because if we actually tried every integer, this is the only question we'd ever be doing for the rest of our lives, right? So we're going to create a proof using generalizations, using algebra. So we'll start by letting x be equal to any integer, because that's what we want, this to work for any integer. Then we have to set up the sum of 5 consecutive integers. So let's let s equal to the sum of 5 consecutive integers. Now, I understand using s's and 5's are kind of confusing, so I'll try to make sure that my 5's look more like 5's and my s's look more like s's. So how do I write consecutive integers for x? Well, let's make x the median number, because that's easy to multiply by 5. So two values that are bigger than x, the next consecutive one would be x plus 1. So you can substitute any integer for x. So if x is 3, x plus 1 would be 4. So how would I get 5? Well, I would have to have x plus 1 and x plus 1 again, or x plus 2. So that if this was 3, the next one would be 4, the next one would be 5. So if I go the opposite direction, I would need 2, so that would be like x minus 1. And another one would be x minus 2. So we're just setting it up so that you can see x, x plus 1, x plus 2, x plus 3, x plus 4, and so on. We're seeing those consecutive integers, so we're setting that up. I just set it up so that x was the median number, because then that's an easier one to deal with. Now, let's simplify this statement. So collect all my x's. I would have, we'll get rid of the brackets first. So x minus 2 plus x minus 1 plus x plus x plus 1 plus x plus 2. All right, and then collect all the x's. That would be 5 x's. And then negative 2 minus 1 plus 1 plus 2. Well, the negative 2 and the plus 2 cancel the negative 1 and the plus 1. So I'm left with the sum being equal to 5x. Well, look at that. Our median number is x. We'll highlight it. And our answer is 5x. So this is a proof, but you can't have a proof without an explanation to go along with your math. Just explain what you did. So we can say that since x represents the median, of 5 consecutive integers, I can write out the word 5 if it's easier. $5x will always represent the sum. So John's conjecture is true for all integers. Oops. All right, look back and see what we've done. So we had this conjecture by John. We agreed that with his examples it worked. Then we tried a bigger one and saw, well, looks like it's going to continue to work. And if it's going to continue to work, how can I use algebra to generalize this and to make it work for all integers? And so we used x, and we set up 5 consecutive integers using x. We proved using algebra that the sum would be 5x, and then we wrote an explanation to justify our proof. So that's what proving conjecture is all about. Now, every proof that you do is going to be a little bit different and is going to require something different from you. So you're going to have to do lots of practice in order to see what types of proofs you're going to be looking at. Okay, let's take a look at the next page here. So what type of reasoning did John use to make his conjecture? John used inductive reasoning. He analyzed a pattern and developed a conjecture about this pattern. We used deductive reasoning to prove John's conjecture. How does this differ from the type of reasoning that John used? So we were able to show that the conjecture was true for any 5 consecutive integers, and in fact we were able to prove that the conjecture was true for all cases. John, using inductive reasoning, was only able to say that the conjecture was true for specific sets of consecutive integers that he sampled. So deductive reasoning means that you are proving for any case, whereas inductive reasoning, you're just taking a set of examples and showing that it's true for those ones. So here, deductive reasoning, drawing a specific conclusion through logical reasoning by starting with general assumptions that are known to be valid. Now, does that mean all conjectures are true? No. We're going to have invalid conjectures too, and I'll show you how to handle those as well. All right, let's try another example. Example 2, using deductive reasoning to make a valid conclusion. All dogs are mammals. All mammals are vertebrates. Shaggy is a dog. What can be deduced about Shaggy? So we know that all dogs are mammals and all mammals are vertebrates. So if we drew a Venn diagram, and a Venn diagram is just a graphic organizer where we can see what's happening. If I drew this Venn diagram and called the big circle vertebrates, I think everyone would agree that mammals are vertebrates, right? So let's put that inside. So this would be mammals. And again, we would all agree that dogs are a type of mammal. So that would go inside here. So we can see that dogs are mammals. Mammals are vertebrates. So can we conclude that a dog is a vertebrate? I would say yes. So using deductive reasoning, Shaggy is a mammal and a vertebrate. And that's all we need for that type of question. Let's take a look at example 3. Example 3. Using deductive reasoning to prove a conjecture. It says prove the product of an even number and an odd number is an even number. Alright, so let's start by letting A be even. Let's just write A be an even number. And B be an odd number. Now, for a number to be even, it must be divisible by 2. So let's say that A is equal to 2n. Okay, so that's our even number is 2n. And B is a different odd number, so let's call it 2m plus 1. Right? Because an even number has to be divisible by 2, where an odd number would not be divisible by 2. Now it says prove that the product of an even number and an odd number is an even number. So we would want to multiply these together. So A times B would be 2n times 2m plus 1. Remember that n and m are integers. So this would be a times b. If we multiply this out, that would be 4mn plus 2n. If we look at each term here, we can see that they're both divisible by 2. So let's factor out a 2. And if we can factor out a 2, then we're saying that AB is an even number. So AB, we can take out the 2, and you'd be left with 2mn plus n. Well, if you can do that, right, that means that AB is even. So therefore, since AB is divisible by 2, AB is even. And we've proved that the product of an even number and an odd number is in fact an even number. Alright, last example, example 4, communicating reasoning about divisibility rule. So this is similar to what we just did. It says the following rule can be used to determine whether a number is divisible by 3. Add the digits and determine if the sum is divisible by 3. If the sum is divisible by 3, then the original number is divisible by 3. And you might have used this in elementary school when you were talking about dividing. So they're saying, okay, if you take two numbers like 2 plus 4, right, because that would be 24. So your value is 24. 2 plus 4 is equal to 6. Well, 6 is divisible by 3, which means 24 is divisible by 3. If we did, let's say 37, well, that's 3 plus 7, which is 10. 10 is not divisible by 3, so 37 is not divisible by 3. If we do one more, I don't know, if we did 81, well, that's 8 plus 1, and 8 plus 1 is 9. 9 is divisible by 3, so 81 is divisible by 3. So that's the rule that they're talking about. So it says use deductive reasoning to prove the divisibility rule for 3 is valid for a 2-digit number. Alright, so if we know a couple of numbers, let's try a 1-digit number like 9 and a 2-digit number like 27. We know both of those are divisible by 3. So that's our numbers. Now, if we expand our numbers, we can, in words, if you remember how to do this in words, this is 9 ones. So that would be, like numerically, 9 ones, right? Like, or 9 times 1. 27 would be 2 tens, we're kind of looking at place value, and 7 ones. So 2 tens and 7 ones would be 2 times 10 plus 7 times 1. We're just breaking that up. Why? Well, if at this point we can let AB represent any 2-digit number. Okay, going back. They want to say that this is valid for 2-digit numbers. Why did I do a 1-digit number? Just to show you the place value, how that works. So we're going to let AB represent any 2-digit number so that we can prove this for any number divisible by 3. So if we continued with this pattern, AB is my 2-digit number like 27. So A would be my tens and B would be my ones. So I'd have A times 10, B times 1. Okay, so I basically modeled the same thing I did at this level, but with AB instead of 27. All right. How does this help us? You got to keep going here. So if AB is 10A plus 1B, right? That's what this is. I just simplified it because the number is usually in front of the letter. Then that means that AB is 10, oops, that's an 11. 10A plus B, because we don't need that 1 there. Well, let's break that 10A down. So AB is equal to, 10A is the same as 9A plus 1A. Everyone would agree that 9A plus 1A is 10A. Or we could say that AB is 9A plus A plus B. Okay? Well, plus A plus B, I'm just going to take that A plus B and put it in brackets. So 9A plus A plus B. Why am I doing all this? Okay, well, have a look at this again. AB, my 2-digit number, is going to be equal to 9A, right, plus A plus B. That means that the number AB is only divisible by 3 when this part in brackets is also divisible by 3, because we can see that that 9 is already there, so we know that this is divisible by 3. It's already divisible by 3. So we want this to also be divisible by 3 in order for it to be valid. Okay, so we can write our statement. These notes are just for us. This is where we would end the proof, right? Where the AB is equal to 9A plus A plus B. So therefore the number AB is only divisible by 3 when you add those two values, A plus B is divisible by 3. This isn't intuitive. We wouldn't know from the beginning that this is what we were supposed to be doing, right? But showing you this type of proof, now you can apply this to other situations. So it says, go back to the beginning, add the digits and determine if the sum is divisible by 3. So you're adding A plus B, you're adding those two digits to see if it's divisible by 3. That's exactly what we're saying in this proof. That's it for today's lesson. Thanks for joining me.